Okay. Welcome everybody to this new episode of the podcast Coffee Breakdown. Today we have with us Dr. Pedro Viegas, who's currently postdoctoral researcher at the University of Lisbon in Portugal. And Pedro is also a good friend of mine, and he's also a colleague. We met, in fact, in the Netherlands. So I want, first of all, to thank you, Pedro, for accepting the invitation and to share with us your thoughts.
Hi, everyone. Hi, Luca. Yeah, thank you for introducing me, and thanks for inviting me. I'm happy to be here.
Okay, great. Well, let's start maybe with the usual questions. I would like to give you the floor in a couple of minutes if you can introduce yourself, what you studied and what you have done in your career. And also, if I may, I have some bit more personal question. I know you work in different labs around Europe. And do you think like working in different countries gave you a broader perspective in something like scientific thoughts? Or it would have been better to have more continuity in the same lab? This is also interesting for me because I'm starting my career as well.
Yeah, so yeah, as we know, young researchers today are doing that a lot. So like doing masters in one place and then doing the PhD in a different one, and then a postdoc somewhere else, and then another postdoc somewhere else. Maybe hoping to get a permanent position at the end at some point in academia, or maybe leaving at some point for industry is also good, of course. So yeah, in my case, I had done my studies in Portugal, then went to France first for Erasmus, and then for PhD at LPP in École Polytechnique, then the postdoc. Well, so in France I worked mostly on jets, on modeling helium jets, so we'll talk maybe a bit about that.
Yeah.
Then in the Netherlands, a postdoc working on modeling plasmas for CO2 conversion. So that's where I met you. And then I was in Czech Republic, in Brno, and then in Lisbon. So well, a bit continuing working on the same subjects, but also with some variety, with some new additions, of course. So yeah, we work in different groups and often in different countries, right? There are pros and cons to this. So there's a part that is very exciting and very productive. So we at each place we meet new subjects, we meet new groups, work with different people. And at each place there are different expertise, both technically and scientifically. So we learn a bit of this. There's also different ways of working in different groups or in different institutes. So we learn and we compare. So we start seeing what works better, what kind of work what works better in each place, and also on the personal side. You get to make friends a bit everywhere, and you get
That's true.
different cultures. But there's also, in research, it's usually a long-term effort. So when changing places, there is, on the one hand, an element of continuity because you accumulate knowledge, you accumulate experience, but there's also an element of rupture. So at each time, it's kind of restarting a part of your life. At each time, there's a bit of a new start on your personal relations, so making new friends, but also on getting to know a new group at work and getting to work with them. And so the downside of changing a lot is to get to the most productive results in research, we need some time. We need to get to know the techniques that other people are using as well, and we need to develop our own tools, and we need to develop our expertise in the scientific field. So I would say yes, at beginning of your career, changing is very good. You can learn a lot, but at some point, I think you feel the need to extend and to be able to develop your own for a longer time.
Yeah, that's true.
Yeah, each person adapts to this differently, of course.
Yeah, that's true. Okay, that's a very good answer. Okay, thank you very much. Okay, I think we can. It's actually a very interesting topic. I would continue this discussion for longer, but I think we can jump in straight to
Of
the
course.
scientific part. Maybe you can tell us a bit more about plasma jets. In my view, you're one of the experts in our community about jets. You recently wrote a review paper, and you also had an invited presentation in this online low temperature plasma seminar. So also for people who don't know this topic, can you introduce this type of application? Or,
Yes.
yeah.
Yes. So we call jets to plasmas that usually develop inside thin dielectric tubes or capillaries, and then they propagate. So there is a kind of discharge that we call ionization wave, or just streamer discharge that that is not homogeneous. It is propagating. So there's a velocity. So through time, there is a front of propagation that evolves like a wave. So this plasma can develop inside these tubes and then propagate into air. Meaning that you get a plasma in an open space at atmospheric pressure and at room temperature. And this means it's very practical for to apply on any surface, really, because you don't need a vacuum pump, you don't need the container. Usually you need a noble gas to be able to do this at atmospheric pressure. But this means you can apply the plasma wherever you want, and this includes biological tissues, biological surfaces. So that's the main interest of
Okay.
jets, why they became so popular.
So one of the main application is probably plasma medicine in that case, right? Or treatment of
Yes,
tissues.
there's surface
Oh, yeah.
functionalization at atmospheric
Okay.
pressure, because that's all. There's also an interest to, I mean, plasmas are already used to treat surfaces, but to be able to do it at atmospheric pressure is also interesting. And then for plasma medicine, so things like wound healing, sterilization, the apoptosis of cancer cells. So of course other plasmas can also do this, but the jet has the advantage. Okay, you can use this tube to get the plasma to the place where you want.
Okay. And in some cases, sort of it's a bounded discharge because it's in contact with the surface. This is probably one of the difference than natural streamers, for example, right?
Yes. So one difference is we are inside the tube, and the other difference is the working gas. So
Okay.
typically streamers were studied in air or in air gases like nitrogen, and the jets typically noble gases are used because these are the easiest to ionize at atmospheric pressure and to have a controlled and cold discharge. So to keep it at room temperature, usually it's used helium or neon or argon, but even there can be some heating. But if the goal is we need to keep it room temperature to not destroy the biological tissues, not have a destructive plasma, then yeah, noble gases are used in jets.
Okay. Then you did, from what I know, modeling work and also comparing validation of models with experimental results. So first of all, well, typical question is how do you model this type of discharges? When we are talking about model, we're also talking about assumptions, of course. So what are the main assumptions underneath these models? And yeah, I would maybe start with this.
Yeah. So this discharge, as we were describing, well, they are very thin on the radial direction, and also, as I was describing, there is this wave propagation in the axial direction. So in the simplest case, we can have a system that is axisymmetric, because this tube is radial symmetric, and then the propagation in air can also be radial symmetric. But still, we have sharp gradients in the radial direction and the axial direction. So in the simplest case, we can have sort of sort of a
2D.
device model, so a model for the whole geometry with 2 dimensions axisymmetric. Then if we gets more complicated geometrically, I mean, then we need 3 dimensions if we lose the axial symmetry. But well, to study the physics, yeah, we need a model for discharge physics. So usually for plasma physics, we always have this choice: fluid or particle description, or hybrid, and then the dimensionality, right? So for the case of jets, I already said 2D axisymmetric to be able to have these radial and axial gradients well described, and then at atmospheric pressure, the fluid models should work well. So the fluid model based on the moments of the Boltzmann equation, and then conservation equation for mass, momentum, energy. So this is one part of the description. So this is good to describe charged particle movement in the gas phase. But then in the jet, we have a lot of surfaces because we have the plasma inside the tube. It's interacting with the tube.
Yeah.
There's some electrodes generating the plasma, so the electrode can be placed inside or outside the tube. And usually, well, the jet, I mean, it can be studied without a target surface, so as a free jet, as a plume, but the jet is used on surfaces to treat surfaces.
Exactly.
So there's also an interest to describe the plasma interaction not only in the tube, but also with the target surface when the jet is propagating in air. And this means, so on the one hand, well, Poisson equation for to describe the spatial distribution of electric potential and electric field, as in a lot of other plasmas. But then also the interactions on the surface, the boundary conditions there. So what species we expect to be bounded from the plasma to the surface, and especially with charges. How likely is it that electrons from the plasma become absorbed and part of the conduction band of surfaces, or how likely is it for electrons from the surface, from the material, to be extracted, to be emitted from the valence band back to the plasma. So the model has to take all this in consideration, and not everything is known, of course.
Yeah. So this is interesting because, of course, as plasma physicists, I feel we are very much focused on description of the plasma state, maybe its evolution in time, right, through solution of this differential equation, as you were mentioning, the fluid model. So you think it's also equally important to have a model that describes the time evolution of the surface states, because since there is this mutual interaction, right? So if you have a very accurate model of the plasma, but not a model of the surface state, or the evolution of the surface changes because of interaction of plasma, maybe the overall model of the system is not very predictive. What do you think? Is it important, or maybe a second order correction?
No, I think in a lot of plasmas it's important. So okay, if we just want to know if we're very focused on the volume processes, and for instance, if we have a plasma that is very homogeneous in space and we don't expect the surface to have so much influence, then okay, we can just focus on the volume. And then we focus a lot on the chemical processes as well, and well, let's say local processes, everything that happens only there. But in the reactor, in plasma devices, yeah, there's always a surface somewhere. And now we were talking about jets. This is an example where surfaces are important. So in a lot of cases it's not secondary. We really need to also have knowledge on what happens on the surface. So the surface is affected by the plasma. The plasma provides a reactive species to the surface. It provides electric field to the surface. It provides charges to the surface. It can provide radiation to the surface. But the surface is also affecting the plasma, right? So the surface can be extracting, in a way, some species from the plasma, and these will have an effect on what collisions take place in the plasma and the dominant effects. So from the application point of view, we can see this as a synergy. We can try to take advantage of the best properties of some materials and the best properties of some plasmas to make some catalytic effects that are beneficial. But also from the physical point of view, yeah, I think to understand things better, we need a self-consistent coupling between plasma description and the surface description. And I think there's room to improve there, to know more there on the plasma surface interaction.
Okay, very interesting. Thank you. So, and if we're talking about the validation of models with respect to experiments, and of course, you know, as people doing modeling, we would like to have a lot of experimental data that are well characterized, also in terms of conditions. So do you think, so would it be important also like efforts in data sharing, for example? And how details we need to describe? Because you know, from my limited experience of modeling also plasma surface interaction, also the description of the surface, what happened before the application of the plasma is very important. And if you're talking about the biological system, also maybe the description of the environment is important. What is the level of humidity of the light? Because I don't know, you know, so it becomes exponentially more complicated, right? So I don't know. I don't know. So you think, what is the strategy that you see in model validation? Do you think like data sharing could be very important, or which level of details we need?
Yeah, I think you're right. We are evolving to more complex systems with more and more variables. So maybe let's go back to the jets to start from that example.
Yes.
So okay, in the jets, there's one part of research that is very focused on application, and in that case, it's all about, okay, we describe what conditions and then what output is obtained. So if we have this jet in these conditions, then we were able to obtain this effect on cells or on apoptosis or whatever. But then for physicists, we want to characterize more the physical quantities in detail, right? And this was done typically via simulations. So simulations were able to give this spatial distribution of electric field, of electron density. So just to talk about some of the main quantities and also the chemistry, the species. But there have been a lot of important development on the experimental side. So for instance, these two quantities I mentioned, electric field, electron density, in the last decade, there are more techniques to measure them and to measure them with spatial and temporal resolution. And these very exciting for modelers for validation. So to test the models, to validate, see what we're doing right, but also to notice what we still don't know, what we're still unsure of.
Okay.
Yeah, and we well, you mentioned our work on the review on physics of jets. We did this. We searched for the data to be able to compare from different works what values of electric field, what values of electron density are being measured, and then to be able to compare also with, when we do the simulations, to compare also with the whole ensemble of measurements that were done, but also we need to take into account what are the conditions, right?
Yeah,
so
exactly.
that relates with your question. We need access to data, but we also need to understand well what are the conditions, what are the techniques, because you know, from this comparison of simulations and experiments in jets, we found, for instance, I liked a lot working on this because we were able to show the community what we know, what we should trust. So for instance, the values of electric field in gas phase, but also inside materials that are pretty well validated. So there are several experiments and the simulations providing and agreeing on the results. So we can say we can trust this. Then we have also cases where we have more uncertainties. We are more unsure about results. And we saw this, for instance, with electron density. We see orders of magnitude difference in different measurements and simulations. But when we dig deeper, we see, okay, the conditions are also different.
Exactly.
So we need to be really clear. We need to be really clear. Okay, there's this wide range of values, but also assess, okay, the conditions have a large influence, but this also means that we don't have enough data for the same conditions. So one of our conclusions was, okay, sometimes we need to focus for the same conditions, have different techniques, assessing the same quantity, have the simulations as well. And there we'll be able to see also if the techniques are measuring different things.
Exactly.
And then we need to think, why is that? Or if the simulations are providing a different result, why is that? To, in the end, be able to say, okay, this is the range of values we should have, and we trust it. We're confident about it.
Yeah, that's very true. So yeah, but this is what I mean also with the question, right? So of course we need to advance with models, with experiments, as you mentioned. Probably we also need a sort of strategy that tells us, okay, what are the minimum quantities that we need to know, minimum sufficient quantities that we need to know to fully characterize a system. For example, if I'm talking about jets, and I measure electron density, but I don't know anything about the surface that the plasma is in contact with, maybe is not enough to describe the system, So I need also information about that, and the other way. So for different type of discharges, I would think that this is important. There are different quantities that needs to be detailed described, and there is a minimum set probably. I don't know. And as a community, I think we didn't define very well what are the. Of course, if you ask people, yeah, electron density is very important. It's like, is it sufficient to describe a plasma jet if I measure only electron density? I don't know.
No, it's not. It's not.
Also,
you need, well, for sure, the excitation source. So how is this plasma being generated?
Okay.
And for sure the dimensions. And well, in some cases the flow rate can be important. And then, as you were saying, also the surface. So so yes, there's quite quite a lot of metadata that is necessary to describe a system. And earlier you were saying, okay, the particular surface, what is the history of the particular surface? Also, its memory can be important, and that's something, for modelers. Okay, maybe sometimes we don't value that because for us, the surface is in the computer. It can be always the same for us, but then our experimentalist colleagues will tell us, no, but this surface was used before, while the other one was a new surface. And this kind of detail can make a difference.
Yeah, true. Also, talking a bit, going back, talking about the model, still on plasma jets. Of course, we can expand if you feel, but so what do you think, which direction do you think the research is going? So which advancement in the model do you see coming in the next year, or which improvements you think are important? I don't know, maybe coupling of gas flow and plasma. I don't know. Maybe there are some really important things that and more generally, I would like to ask you in a bit general sense, not only on jets, like, why do you think we need advancement in the modeling, right? Because rarely you see, I mean, the theory is there. We know the theory of fluid modeling, we know the theory for kinetic modeling and so on. And I think and we know how to solve differential equations. So why do we need better models in terms of robustness, in terms of fidelity, and so on?
Yes. So one side, on the one hand, we want to move to more predictive modeling, right?
Yes.
We have a lot of plasma reactors with their complexities, rather complex systems, and if we don't want to test, I mean, usually we cannot experimentally test every possibility, right? So if we have a predictive model, the model can tell us what happens when we change a parameter, which may not be easy in the experiment. And also in the experiment, we cannot measure as much as we can simulate, in the sense that some quantities are not easy to be measured or with spatial resolution or temporal resolution that we can have in simulations. So the model can be very useful. And so on the one hand, there is these efforts for predictive modeling that is not in itself about new physics, right? And I think that that's what you were saying. And when we think of predictive modeling, okay, we know from experience that yeah, we need to get rather complex to get there, because yeah, me and you, we worked on modeling plasmas for CO2 conversion, for instance. Okay, we did some progress with the zero-dimensional models. We were assessing in detail what is happening in the core of the plasma. So in this case, we are really focused on the volume process. Well, the gradients we assume the gradients should be smooth, and we assume we can study what are the chemical processes, what are the important ones, how much they depend on other quantities, like or local quantities like reduced electric field or gas temperature. But then we saw, okay, there are sharp gradients also in the radial direction. So then you did, for instance, this 1D radial model where we describe this gradient, and this was very interesting. But you know, the 0D modeling, the 1D radial were not enough to get predictive.
Yeah, exactly.
And yeah, in that case, and that happens in a lot of plasma reactors. In that case, we had the microwaves, you know, propagating without radial symmetry. We also had this vortex flow that doesn't have to be radially symmetric. We had the turbulence transport emerging that doesn't have to be radially symmetric. So we think to get predictive modeling of such a reactor, we need to go to D.
Yeah.
And we need to couple all these elements of physics, right? So we have the transport of charged particles, which is what we usually have in plasma models. This can lead also to charge separation, and therefore to the description of a relation between electric field and charge separation, so Poisson equation. But as I mentioned, we also had Maxwell's equations with the microwave. We have this complex flow. So one part of advancement is this coupling between the different physics to reach predictive capabilities, because all these elements I mentioned, they will determine the reactor output and the distribution of the species of interest, of CO, of oxygen, etc.
Yeah.
And in the jets as well, we know the plasma can have an effect on the flow due to heating or due to electrohydrodynamic force. So also there is an effort needed for coupling plasma model with flow model, with thermal effects, with turbulent effects as well. And also on jets, there is an effort to understand longer timescales, because in a lot of plasmas, jets included, there are these pulse conditions. So these repetitive conditions is not a steady state.
Yeah.
And what happens between pulses, between the repetition of plasma, matters a lot. And models typically are not always addressing what happens in between pulses, because what matters is what happens in one discharge, right? But this is one of the conclusions we took also from the study of jets, is the uncertainty still on what we call memory effects. So the leftover charged species, leftover reactive species on volume or on surface that will have an influence on the next discharge. And so this means, you know, models with more computational efficiency for the longer times, also with efficiency to manage three-dimensional geometries and the coupling between different elements of physics. But then I also want to reach the other side, which is, okay, the theory of physics is well known for the volume, I would say, as we already mentioned.
Yeah, true.
So the transport of charged particles via the moments of the Boltzmann equation, as we already talked. But I would say there's still a lot not known on, for instance, on collisions. So when there is a collision, even in gas phase, we don't know a priori the cross section. Of course, it can be calculated, but we also, we don't know exactly the intermediate states. We know the initial state of a reaction and the final state, but the atoms, the molecules, they can be undergoing changes through different electronically excited states, for instance. So the clouds of electrons can be rearranging around the atoms and the molecules during these collisions, and these we don't know a priori, and even the current models, they need to take some assumption on initial and final state, right?
Yeah, true, true.
So there's still some fundamental knowledge there, and that's collision physics, let's say. But also what we already talked about, all the uncertainties on the surface, that that maybe the knowledge already exists, maybe more on the solid state physics community.
Yeah, that's
and
true.
And then to have the knowledge come back to the plasma community, I would like to come again to this effort of self-consistent coupling between
Yeah,
surface more microscopic surface models and the plasma models. And this means, descriptions like Monte Carlo on the surface, but also like molecular dynamics, density functional theory, electric double layer models.
yeah.
So there's this whole variety of models that can be explored. So our field becomes very technically diverse, right? To be a modeler in plasma physics is not just the moments of the Boltzmann equation. Then we
Exactly,
need
exactly.
a bit of particle description, a bit of fluid description, a bit of other fields of physics. Um, so I would say, okay, we want to advance models because of the predictive capabilities, but we also want to advance models for our understanding of physics. Because, okay, a lot is known, but some particular issues and particularly some coupling of different fields is not yet fully understood.
Yeah, that's very interesting. So in fact, it may be that for having predictive modeling of some plasmas, we need intrinsically this cross-pollination with different fields, right? You mentioned solid state physics, but also maybe computational fluid dynamics. You mentioned this 3D and coupling with gas flow. I think as plasma community has to learn a lot, probably also from that. That's very interesting. And still, we can learn a lot also from lower dimensional models like 0D, maybe that are a bit more robust, but do not include accurately, or they're not very high fidelity, let's say. We cannot do like engineering type of studies or optimization, probably. That is true.
Yeah,
Okay, okay.
I agree. It really depends on what we want. So yeah,
Okay.
for the engineering, for the applications, for the predictive modeling, yeah,
Yes.
the efforts are for going to higher dimensions. But I think we already mentioned, if we really want to go into detail on what happens locally, then we can really focus on 0D, and that allows, to get rid of the computational cost of everything else. So it allows to isolate the particular part of physics that we want to study.
Yeah, 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 yeah.
Yeah.
That is true. That is true. And in my opinion, I say it in a bit simplificatory way. There are kind of two axes. One is the sort of fidelity of the model. So if you increase the dimensionality, you go 2D, 3D fluid model, for example, you increase fidelity for modeling plasma jets or maybe CO2 microwave discharges. On the other axis, there is a sort of robustness of the model for different conditions as well. So of course you would like a model that you run in different conditions and it's always stable numerically, for example. And maybe there is also another axis that is the computational cost, right? Because, for example, I don't know, fully kinetic models are very robust and very high fidelity, in my opinion. But if you want to go 3D, with a particle in cell, for example, it's very computationally demanding. So we need to take a lot of factors into account. So there is also computer science. I don't know. It's very complicated.
Yeah. I mean, so far I was focusing the modeling discussion on the physics, right? But it's true. I mean, advances on modeling are both on the physics and on the numerics, right?
Okay.
And yeah, so I mean, technology is evolving. We have access to more and more performant CPUs and GPUs. Um, but we still need a lot. Well, we need a lot. I think the applied mathematics, right? So these people that develop tools, that develop mathematical schemes that we can apply to solve our physical equations, and we need these, to be performant, and as you said, to be robust, to be useful for different conditions that we want to study.
Yeah. Okay. That's very interesting. Okay. To conclude, are there some other areas, some other application besides plasma jets and CO2 conversion you were mentioning that you think are interesting? You still in the plasma physics or plasma chemistry world that you saw at conferences and you think, okay, this may have an interesting development in the near future. What do you think?
Yes, I mean, there's so much that that other colleagues are doing. For sure. Well, I like a lot the physics when I hear about the discharges in liquids, for instance, where we need to approach when we need to approach some different physics, in the sense that all the gas phase assumptions are no longer necessarily true. So, well, that's one subject. Well, there's a lot of interesting stuff. Well, I'm particularly interested when I see some papers or some conference talks on the plasma surface interactions.
Yeah.
So it doesn't have to be jets or CO2, but anytime someone is trying to go deeper and trying to understand better what happens between between charges and surfaces, or even what effect charges can have on the bonding of different particles to the surface. But there are, of course, a lot of fields also for industry. So for material treatment, this keeps evolving. So for instance, these atomic layer deposition assisted by plasma is a field that still has room to grow, I think, industrially. And it's very challenging because it's atomic layer deposition. We really want to control very well the processes. Then there are other fields I know less well, like etching or other forms of deposition that have interesting physics behind as well. And we always see, also these actuators. So the fact that plasma can be used to have an influence on flow, and this can be used, well, for instance, in the aerodynamics industry. This is very interesting because it touches also this point I already mentioned on jets. So the fact that the plasma in the jet affects the flow outside of the jet, and therefore affects the gas composition in the jet, the temperature. This has application on other fields. So as I was saying,
yes.
these actuators, this means we always need to take into account on different surfaces, on different geometries, these effects of that the plasma can have on the flow, and vice versa.
Yeah. Okay.
These are just some examples.
Okay, very interesting. Okay, thank you very much, Pedro. I really enjoyed this conversation. It
Yeah,
was
me too.
really interesting on different topics, and I'm sure we keep in touch, and good luck with your work and your future. Thank you.
Yeah, thank you. You too. Thank
Yeah,
you. I was happy to be here. Thanks.
bye.